Welcome back. So, we're in the part of the course that has to do with life as defiance. And what I need to do is, in order for the very idea of life as defiance to make sense, I first have to show you about the universe as compliance. And when I say compliance as opposed to defiance, what I mean is that there are certain strictures that tell natural processes where they must go. And this is codified in the form of the famed second law of thermodynamics, which says that systems shall evolve towards their state of maximum entropy, and or if you like, from a more subtle point of view, to minimize their free energy. I'm not going to go into that distinction right now. It means ultimately the systems will go towards their more probable states. In that sense, it's almost a triviality. What I mean by that is that, as we've already talked about in the previous vignette, the system has the possibility of existing in a bunch of different states. And it turns out that the macroscopic thing that we observe is the one that can happen in the most microscopic ways. And I gave you the example of the molecules in the room in which I'm sitting, in which I said you could imagine all the molecules going to one side of the room, dividing the room in half, two sides, and the probability of a given molecule being on the right-hand side of the room is a half. The probability of two such molecules being there is one half to the squared, which is 1/4. And to get all three molecules all on the right-hand side, the probability of that is 1/8. And so at any rate, this system will evolve towards its most probable state, the state that can happen in the most ways. That is the edict of compliance. And what I'm trying to say in this whole section of the course is that, in fact, life finds ways to contravene that edict. It says, well, maybe at the level of the whole universe, yes, indeed, the entropy is going to increase as a result of the direction of spontaneous processes. But if we happen to look just at one part of the system, for example, remember I showed you the film strip of what was apparently concentration going up a concentration gradient. If I show you that without showing you the concomitant use of a pump, there's a pump, it can consume energy. If I showed you a video of what happens in a refrigerator after I turn it on, you'd say, well, that's weird because you're taking heat from a colder source and putting it out into a hotter source. And that's true. And I've got the refrigerator plugged in. And so, it's basically a heat engine running in reverse. I have to consume energy in order to do that pumping. Then there's no problem. It's just that when you look at only the refrigerator or only the cell with its concentration gradients, you'll say that seems like the natural process is going in the wrong direction. So it's going to take me a couple of vignettes to set up the whole picture of equilibrium so that we can then start to dig into the ways in which biological systems, living organisms, contravene those ideas. I hope that's a word, contravene. Maybe it's not. So the first thing this particular vignette is really about thermal energy, the thermal energy scale, and what we can do with the thermal energy scale, or how should we think about it. So I already argued that the thermal energy scale, one way to think of it is that the energy of a given molecule, for the moment I want you to think about the gas in the room where you're sitting, the energy of a given molecule is 1/2 mv squared, and that's equal to 1/2 kBT, where T is the temperature of the gas molecules in the room. And so at room temperature, 300 degrees Kelvin, as you see here, kBT is 4.1 times 10 to the minus 21 joules. That's roughly 4 piconewton nanometers. And as I say here, that's the natural energy scale of cells and their molecules. So I wanted to say a little bit about this notion of the thermal energy scale, and I want to do it with reference to the Boltzmann factor that we've already used several times. So I remind you, let me add a page here so I can do a little bit of calculating. So the reminder is that the law of Boltzmann, I'm going to call it the law of Boltzmann, tells us that if we want to compare the relative probabilities, so relative probabilities of two states, microscopic states, that have energies E1 and E2, so that's important. Then that's going to be given by e to the minus beta E1 over e to the minus beta E2, where that's the probability of the state with energy E1 over the probability of the state with E2. And the reminder is that beta is defined as 1 over kBt. So what do I take away from this? Well, what I take away from this is that the relative probabilities are determined by a dimensionless ratio. So the conclusion is that the dimensionless ratio, E over kBt, determines the probability of a given state, of a given microscopic state. And what I want to do is I want to use, as an example, I want to use the example of levitation. So let's consider me levitating. So if I were in the classroom with all of you right now, what I would do is I would sit on the table at the front of the room and I would levitate for you. And what I would do is I would attempt to levitate to a height of 1 micron. And let's work out the probability of me levitating to a height of 1 micron. So the probability of h equals 1 micron divided by the probability of me just sitting on the ground, which is 0 microns, is going to be given by e to the minus mgh over kBt. The reason for that is that my potential energy, if I exercise this 1 micron excursion, is going to be given by mgh. So we can work out mgh over kBt. How do I do that? Well, in my case, that's 100 kilograms times 10 meters per second squared times the height of 10 to the minus 6 meters, and then divided by 4 times 10 to the minus 21 joules. The units are, this is now dimensionless. You can check that. Just remember that work is force times distance. And so I have force, which is kilograms meters per second squared, times distance. So that's why I claim that's dimensionless. And this thing, if I do all the arithmetic, ends up giving me a 1/4, which is incidental and not really worth bothering about. And then I have a 10 to the 21, 10 to the 22, 10 to the 24. So this gives me 10 to the 18th, something like that. So the probability of me levitating to a height of 1 micron is e to the minus, I'm going to just call it 10 to the 18th. So I'm no can do. I'm not going to be levitating. But now let's imagine that instead of having the mass that I do, I had the mass of a bacterium, which is 1 femtokilogram. So what about a bacterium? So in this case, the mass of the bacterium is equal to 1 femtokilogram. So that's equal to 10 to the minus 15 kilograms. So I'm going to recover. That means that mgh over kBt, all I have to do is, I had 100 previously, and now I need to basically multiply that by 10 to the minus 17. So what I'm going to get in this case is 10 to the 1 over 4. So this tells me that the probability of levitation of a bacterium is e to the minus 10 over 4. So that's going to happen, actually. And, I always like to say that, every laboratory has an anti-Boltzmann machine. And that device is called a centrifuge. And the point of that is that it basically changes this thing, the G, by, let's say, a factor of 10,000. So if I choose a G of 10,000, sorry, if this becomes 10,000 G, then I'm going to end up with e to the minus 10,000, 10 to the fifth over 4. So no longer am I going to levitate even as a bacterium in that case. So I've been a little sloppy because that's in solution rather than gas. There's a buoyant mass and so on, but the essence of the problem is really the same. So bottom line, I guess I could have just shown you this. So let's see. I don't, this makes me, I'm curious about, this seems like it might even be a mistake, the 10 to the 22. But here's our MGH is 10 fourths. And then this is what I was just saying about what happens if I increase the G in a centrifuge and so on. Um, well, just out of curiosity, did I make a mistake here? So M is 100 kilograms. G is 10 meters per second squared. That's the H. Then I have 10 to the 21, 22, 24. Yeah, I get 10 to the 18. So I'm not sure what this 10 to the 22 is right here. That looks like it might be a mistake. Okay, so let's think about this levitation in the context of a molecule now. So really what I was doing is I was comparing the deterministic energy due to gravity with the thermal energy. And for a molecule, where the mass is way smaller than a bacterium even, we get an even smaller dimensionless ratio, mgh over kBt. And the thing that I'm showing you over here, I like to think of this as the levitation number, is this dimensionless ratio tells you whether you're gravity dominated or thermal energy dominated. What I mean by that is that if the thermal number is less than 1, that means that the thermal energy counts more, if you like, and that's down in this region. And that means that the molecules are going to be jiggling around. If I'm up here in this region, that means MGH is larger than KBT, and so the gravitational term will make that less and less likely. And so interestingly, if you set the scale at which MGH and KBT are exactly equal, what you find is that that corresponds to a height of about 10,000 meters, so roughly the height of the atmosphere. Okay, so what we've been doing, or what I'm now claiming, is that this Boltzmann factor entertains in its exponent this dimensionless ratio, the energy of interest divided by kBt, and that dimensionless ratio tells us about the probability of a given thing happening. So here I just wanted to give you some measures of various biologically interesting numbers relative to kBt. So the first one I like to call the Lippmann number in honor of, I think it was Fritz Lippmann, who worked on the biochemistry of ATP and its hydrolysis. And all that I really want you to take away from that is that the energy scale of ATP hydrolysis is of order, let's say, 20 kBTs. That's the number I would carry around in my head. Hydrogen bonding, the number there is, say, between 2 and 10 kBTs. The energy of a photon, this is very interesting. Maybe call that the Einstein number. That's of order 70 kT. So photon has an energy scale about 70 kTs. The transmembrane potential, which we're going to talk about as one of our defiances, is worth about 4 kBTs. Another way of saying that is 1 eV is 1/40th of a kT. And then down here, I show you what I'm going to refer to as the Jerem number. And this balances electrostatic energies with thermal energies. And this is relevant for thinking about questions like, why do macromolecules in solution get ionized? And the answer to that is that even though, yes, we learn in school about the Coulomb potential, which tends to attract unlike charges, they're allowed to wander away from each other to a distance where that electrostatic energy is comparable to the thermal energy. And that distance scale might be of order a nanometer or something like that. And the last number is what I would call the Hooke number, and just has to do with the springiness of various things in comparison with the thermal energy. So here I give you a collection of such numbers. I'm not going to belabor them right now. I basically just talked about them. But I do want to call your attention to this column over here, which has BNID, which is the bionumbers idea that refers to ID, which refers to the bionumbers database where you can look up various numbers. So just a few more thoughts. Again, this little vignette is just trying to come to terms with the nature of thermal energy. And I just wanted to point out that, this is the thermal energy scale right here at 4 times 10 to the minus 21 joules. And then what I'm showing you is the energies of other processes or other kinds of situations as a function of their length scale. So let's take the electrostatic energy one. There's a self-energy to putting together a collection of charges, and it costs a lot. If I were to ionize 1% of my charges, I would have a huge amount of energy associated with bringing it into the volume the size of myself. But on the other hand, if you take an object the size of a virus and you have a little charge on it, the energy scale of that is much lower. And so the claim that I'm making here, this is something that Steve Quake and I thought about maybe a little more than a decade ago. There's kind of a confluence of energy, deterministic energy scales and the thermal energy scales at about the nanometer length scale. That's kind of an entertaining thought, and goes back to what I say in the title, which is this is a world where thermal and deterministic forces meet. I think my last comment is just to say that in general, this notion of dimensionless ratios is one of the best ways for us to peer into the world around us. And we're going to talk about the Reynolds number. We will talk a little bit about the Peclet number when we think about active matter. And I will perhaps say something about what I'm going to refer to as the Langmuir number in thinking about ligand receptor binding. But this is, again, just to capture your imagination and to alert you to the fact that using dimensionless numbers is a very powerful way to learn things about the world around us, and tells us about which processes dominate in different situations. So